Now in this lecture, we will cover reverse mode automatic differentiation. And reverse mode automatic differentiation is actually very important and most related to inverse modeling, which I will talk in the next few lectures. And reverse mode automatic differentiation, just like forward mode automatic differentiation, works by using the chain rule. If you can look back on the slides in forward mode automatic differentiation, you will see that forward mode automatic differentiation evaluates g prime x first. But in reverse mode automatic differentiation, it evaluates f prime gx first. So that's in a reverse mode, in reverse order of forward computation. And this is abstract description of reverse mode automatic differentiation. Unlike forward mode, it aggregates all the gradients from downstreams instead of upstreams, and then it backpropagates those gradients to the upstreams. So how do you do that? By chain rule, just shown as here. You suppose your gradients backpropagated from downstream is partial j. J is your objective function with respect to partial w, and you can use chain rule to backpropagate to each upstream nodes. So let's consider an example. We already constructed the computational graph in the last lecture, and I show the computational graph here. And x1 and x2 and x3 are primitive variables. So in the first round, you backpropagate the gradients from the objective function to the first node, which is exactly 1 because partial z is 1. The next step is to backpropagate the gradients from this node to the next few nodes. Because this node accepts two variables, x1 and x2, so it will backpropagate to x1 and x2 respectively. And you can evaluate these gradients using the chain rule because they, with respect to y3, is exactly 1. So you backpropagate 1, and then also backpropagate 1 in this case. Now you also backpropagate because you have sine operator. This is a sine operator, so the sine becomes cosine. And for this node, then it's a square operator. So the square becomes, no, this is not square. This is a multiplication operator. So the derivative becomes partial z partial y2 becomes x3. And then in the next step, you backpropagate all the gradients. For example, for this node, you just sum up all the backpropagated gradients from downstreams, and they finally arrive at this expression. If you just calculate the gradients by hand, you will find that the gradients is exactly those numbers. So in summary, the reverse mode automatic differentiation reuses gradients from downstreams. Therefore, this mode is very useful for many-to-few mappings, as we saw in the computational graph lecture. And so this makes this reverse mode automatic differentiation very useful for some specific applications. For example, in deep learning. In deep learning, you usually have a lot of weights and biases. That can be millions of weights and biases in some applications. But finally, you will only have one loss function that is just one output of the computational graph. So that's why most deep learning software are built based on reverse mode AD. And you also and this is also very good for mathematical optimization with one objective function. Because you have a lot of variables, but eventually you only have one output. So in reverse modeling, what we use most is this kind of idea, is that we formulate a single loss function or objective function, and then we may have a lot of free optimization variables. So reverse mode AD is most relevant. So this is a summary for both reverse mode and forward mode AD. For forward mode, it is very suitable for the case where you have a lot of output variables, but just a few input variables. And for reverse mode, it is very suitable for the case where you only have, for example, one objective function or very few outputs. And there are also many other interesting topics we will not cover in this lecture. For example, mixed mode AD, many-to-many mappings. When you have a lot of M is very large and N is also very large. How can you compute that efficiently? Then if the computational graph has some special structure, you can just take advantage of the structure and design very efficient automatic differentiation strategies. And another very interesting topic is computing sparse Jacobian matrices using AD. Because Jacobian is nearly everywhere in scientific engineering problems, you want to use Jacobian to solve nonlinear equations or using Jacobian to do sensitivity analysis. And in those cases, usually the Jacobian has some sparse structure. So you want to take advantage of that. That also form a very hot topic now.